So one of the things we're going to need to know as we get into analyzing functions is how to talk about end behavior. And you guys did end behavior last year, but you used some slightly different language and notation for it. I'm going to teach you today this limit notation, and it's just another language for saying the same thing. So you guys learned last year that there's sort of three options for what happens at the end of a graph, right? To the far left and the far right. Either it goes up towards positive infinity, or it goes down towards negative infinity, or it kind of levels out to a particular value. And I believe the language you guys used last year was as x goes to negative infinity, y goes to negative infinity. Does that sound familiar to you? And as x goes to positive infinity, y goes to negative infinity. Did you guys feel pretty confident with that? Here, let me quiz you on this one. If I had you look at the end behavior for this, and I'm covering up what I've got on the sides for a purpose. I just want to see what you guys would call this. If I said, what happens to this graph as x goes to positive infinity? What happens to this graph as x goes to positive infinity? You would tell me y goes to negative infinity, because you can see that as x goes really far off to the right, y is going down forever and ever and ever, right? You feel pretty confident with that? How about if I said, what happens to this graph as x goes to negative infinity? You would say y goes to, if you had to make your best guess, positive infinity. This one's actually leveling out. This one's actually leveling out. What y value is this leveling out to, if you had to make your best guess? Yeah, I'd say about 2.5-ish. Maybe it might get up to 3. Somewhere in that neighborhood, though. Yep, and we would know that better if I had actually drawn a horizontal asymptote on here. Then you'd be like, oh yeah, it's just going to level off towards that horizontal asymptote. Okay, so there's 3 options. I don't know if you guys dealt with this case last year. Did you deal with the case where it leveled off? It was always either going up or going down. Okay. All right, so we got a third case. So sometimes it's going up, sometimes it's going down, sometimes it's leveling off to a value. We're going to use different notation. So let's go back to this one. As x goes to positive infinity, y goes to negative infinity. We're going to use this limit notation this year. I'll give you the y of this. The reason we do this now is to get you used to limit notation before you get into calc, because this gets really important when you get into calculus. Okay, so this is limit notation. And it says the same thing that you guys just said a minute. As x goes to positive infinity, now we write it as the limit as x goes to positive infinity. But as x goes to positive infinity, y is headed towards negative infinity. Okay, same thing, just a slightly different format for how we write it. And again, we want to get you used to this. I'm not going to get into what a limit means today, because that's kind of one of those big things in calculus. We want you to get you used to this notation so that when you encounter it next year in calculus, it's like, oh, I know what that means. So you'll see this pop up in a couple different contexts this year. If we look at this side, we said on the left-hand side of this thing, as x went to negative infinity, the y value was leveling off to about 2.5. All right, so that's limit notation. That's the first thing we're going to practice today. Questions before we practice that? No, so the question is limit just the abbreviation as x goes to this value. Limit has a pretty complex meaning that I don't want to get into in class today. I don't want to steal your calculus teacher's thunder next year. It could be me. No, limit talks about you can't actually get to infinity, so we talk about limits. I don't want, again, let's not get into it right now. Actually, I don't think I've ever been tasked with explaining what a limit means to somebody who doesn't know, so I don't know that I'd be the best person to explain it anyways. If you're curious, come see me outside of class and we can explore it. But again, I don't really need you to understand the ins and outs of what this means. I just want to get you comfortable with using it. Yeah, we will, if there's any misconceptions, we'll fix them next year. But for right now, I want you to look at this and say, hey, what this is telling me is that as this graph goes really, really far to the left, the y value is going to level off to a constant value of 2.5. Okay. Any other questions? You guys think you could pull this off? I bet you can. I'm going to go ahead and work through this first one down below here, and then I'll ask you guys to do the other two on your own. When I do these, when I have to do limit notation, I like to set up the format of the thing first. There are certain parts that are always in the same place. And by the way, this is an established norm. The way that this is set up on your page up here, this is how we write this. Please do not take the freedom of moving things around and putting the x arrow negative infinity to the right or to the left of the thing. It needs to be written in that format, please. So we have two different end behaviors, one on the left and one on the right. So I'm going to just get the format of this thing set up first and just leave out the part that could change on the left and the right. And then I'll just go back and fill in those details. This is a strategy that I use a lot in math when there's some format that's always the same. I do the same thing with the quadratic formula. I always write out the format of the quadratic formula first and then go back and fill in the numbers afterwards. It's just so my brain can focus on one thing at a time. So, all right, let's look at the left-hand side. On the left, x is heading towards negative infinity. And what's the y value doing on the left? Is it going up, down, or leveling off? This one's going up towards positive infinity. So the y value is going towards positive infinity. On the right, x is headed towards positive infinity because we're going to the right. And the y, aka f of x, the y is doing what? Up, down, or leveling off? It's going up also, so also towards positive infinity. So when I read this, I say, on the far left of the graph is going up. On the far right of the graph is also going up. And that's it. So go ahead and take a moment and fill out limit notation for those other two. We'll check our answers, come back together, and then move on to phase 2 of our lesson. Please let me know if you have any questions while you're working here. Does anybody need a moment? Give me the universal sign for 1 more minute. If you need 1 more minute. All right, let's see how we did. This one on the left, so negative infinity for x. What's my y doing? My y is going up towards positive infinity. And for this function on the right, it's going down. So on the right, x is going to positive infinity. It's going down, so y is going to negative infinity. Does that look good? Hooray! Here on the left, so x is going to negative infinity. And what's y doing? It looks like it's leveling off towards that horizontal asymptote. So the y value that it's settling towards is 2. So we just put a number there. If it's leveling off, we put the number where it's kind of settling into. And on the right, y is going towards positive infinity, or x is going towards positive infinity on the right, and the y value looks like it's also leveling off to 2. And there we go. How are we feeling about limit notation? We got this? You'll practice this a few times. Again, the goal here is so that when you have to use this next year in calculus, you have seen it, you're comfortable with it. We're actually going to use limit notation to describe what happens around vertical asymptotes in a later lesson, but we'll save that for a more appropriate time. Any questions before we move on to phase 2, which is parent functions? All right. We're going to be doing a lot with transformations this year, which should be good news to you guys, because from what I hear, you guys are transformation pros. Is that true? Can you look at an equation and say, oh, this is a absolute value function that's been shifted to the left by 3 and down by 5 and stretched vertically by a factor of 2? You guys, have you done that before? And then kind of backwards as well, look at a function and look at how it's been changed and use it to write the equation. We're going to be doing that a bunch. I just want to review, and we will actually spend a whole lesson reviewing that. I know you guys spent like a whole unit doing it last year. We'll spend one entire lesson going back over that again. To be prepared for that, I want you guys to be looking at our parent functions. So there are 8 parent functions that we're going to see a bunch of in this semester, and then we'll add some other parent functions later on when we get to next semester. So I want you to be very familiar with these. So I am going to ask you, I'll give you some time in class today, and then once you don't finish in class today, you can finish up on your own. But to go through and do some analysis of each of these parent functions, just make sure we're super familiar with them. So I will do one with you right now, and then I'm going to give you guys some time to work with a partner or a group of people to finish up the rest of them. When you do get together with your group to finish them up, you may consider dividing and conquering. Like you do these 2, I'll do these 2, you do these 2, you do these 2, and then we'll compare our answers at the end. Or maybe you guys want to work together on a couple and make sure everybody's got it. But we're all going to work as a class on one, and the one that I think is probably one of the more complicated ones is the reciprocal function. So I'll go ahead and tackle that with you guys right now, just to kind of show you what I'm looking for on this, okay? So the list of things that we're going to analyze are up at the top. First thing we're going to do is sketch this thing. So do you guys feel comfortable with what the reciprocal function looks like? Maybe, yeah, a couple of you are air drawing it right now. It has asymptotes, correct? There are 2 asymptotes. There's one at y equals 0 and one at x equals 0. So here's an asymptote at x equals 0. Here's an asymptote at y equals 0. And then there's 2 points. There's 2 key points for this. The key points for parent functions are usually points with x coordinates of 0, 1, and negative 1. Now, can we plug 0 into this function? No. That would break the function, which means 0 is not part of the what of this function? What is the list of things that tells you what you can put into a function? What is that thing called? Major concept from last week, folks. Yes, I heard it once. Somebody say it again, louder. What is the list of things that you are allowed to put into a function? Super key concept from this class. The domain. The domain is what you are allowed to put into a function. Yes. Okay, guys, this is what I'm talking about. This class is not about just about step by step how do we do something. You need to understand what you're doing and how it pertains to the greater picture. So 0 is not part of the domain. I think everything else can go into that function, but 0 can't. And we'll write out the domain in a moment. Can you plug 1 into that function? What would you get if you plugged 1 into that function? You would get 1. Go ahead and put that point on the graph for me. If you put an x value of 1, you would get a y value of 1. So that means the point 1, 1 should be on your graph. Do the same thing with negative 1. If you put an x value of negative 1 in, what would you get out of that function? Negative 1. All right, that's enough for me to draw this function. This function is going to approach our vertical asymptote there and horizontal asymptote there. It's going to look something like that. That's called our reciprocal function. We're now going to go through the laundry list of analyses up above. So let's start with domain. So we talked about this a moment ago. There's one value that cannot go into this function. Everything else is okay. So domain would be everything except for 0. Can you guys write that out in interval notation for me? It's going to have 2 intervals. I'll give you a hint. This one's going to start at negative infinity, and this one's going to end at positive infinity. That's the domain. Those are the inputs that are allowed to go into this function. Basically everything except for 0. All right, how about the range? What y values can come out of the function? Anything but 0. Pretty much the same thing, right? All right, we'll just copy that down again. Are you sure you can't get a 0 out of that? There's no number you can put in the bottom of a fraction to make it equal to 0? If the top's not 0, I guess. Yeah, no, there's not. We can get it really close to 0 if we make this a huge number, but we can't make it equal to 0. Intercepts. In this class, you do not have to specify whether something's an x-intercept or a y-intercept. You're just going to write the coordinates down. And I'll know whether it's an x-intercept or a y-intercept by noticing where the 0 is. This is a weird one, though, because this function has no intercepts. What's next? Asymptotes. Asymptotes. Let me show you how to lose some points on our next test. Vertical asymptote, 0. Horizontal asymptote, 0. Your point value for this problem, 0. Okay. Horizontal and vertical asymptotes are lines. Lines get equations. You got to give me something with an equation in it. Can somebody give me the equation for this horizontal line that goes through 0? Yes? For the horizontal one? The horizontal one would be y equals 0. And then I'm going to come back to you for the vertical asymptote right here that also goes through 0. X equals 0. And you don't have to tell me which one's a horizontal or vertical asymptote. I'm going to know based on the way the equation looks. I know that anything that's y equals a number is a horizontal asymptote. If it's x equals a number, it's a vertical asymptote. Make sure you include those x equals and y equals in there. Even, odd, neither. Now, I don't need you to go through the whole algebraic thing like we practiced in our last assignment. Just look at it and tell me, does it have symmetry about the y-axis? That would make it even. Is it symmetric about the y-axis? No, it is not. Is it symmetric about the origin? That would mean if I flipped it 180 degrees, it would look exactly the same. Yeah. So it has symmetry about the origin. Which makes it an odd function. Sorry about that. Moving forward with continuity, I just needed you to tell me if it's continuous or not, and if it's not, give me the x value where it's not continuous. So this function is continuous or discontinuous? It is discontinuous at x equals 0. There's a discontinuity when x is 0. Is it bounded above? No. Is it bounded below? No. So it is unbounded or not bounded, however you want to write that. What else? Again, these are all listed at the top of the page there. Extrema / turning points. Where were we? Oh, turning points. Any local maxes or mins? Do you see little peaks or valleys in that on that function? I don't. I don't. So there's no extrema, there's no turning points. Our book uses extrema. The book that Central Washington uses says turning points. Same thing. If there were extrema, we would just give the coordinates of them. So for example, y equals x squared is going to have a minimum at 0, 0. Right? Because it doesn't go down below that. There's a... Yeah. All right. All we got left is, increasing, decreasing. Let's look at this graph. Is it increasing anywhere? This is a weird function. It is not increasing anywhere. If I look at this portion right here, it's decreasing for this entire portion, and same thing for this entire portion over here. So it's not increasing anywhere. I'm not going to bother writing increasing. It's decreasing, and we got to give the intervals where it's decreasing. And I would say it's not negative infinity to infinity because it's not doing anything here. So our decreasing is basically going to be the same as the domain, because at every point on this graph it's decreasing. So negative infinity to 0 and 0 to infinity. Not increasing anywhere. And then finally, end behavior. And we just learned how to write end behavior. This graph's doing the same thing on the left and the right. It's not going up, it's not going down, it's leveling off to a value. So let's write the end behavior. What's the special y value that we're leveling off to on the far left and the far right? 0. And that's it. So I'm going to give you guys some time right now. Couple of hints, because I'm anticipating some common questions. There is one of these parent functions where the end behavior only contains one limit statement, because it only goes off in one direction forever and ever. The other direction it stops. Can you tell me which of our 8 parent function only has a limit behavior on one side and not the other one? Ooh, I lied. There are 2 functions where it only has a limit notation on one side. Nicely done. One of them is the square root, because the square root goes off to the right, but it ends at 0, 0, right? And the logarithm does also. Logarithm has a vertical asymptote at 0 and goes off to the right forever and ever. If you need help graphing these, remember that you can graph ln x. If you're not sure how to graph ln x, there's an ln button on your calculator. So you can graph ln x. And then I want to show you how to graph the absolute value, because eventually you will have to do that. You might have to do that for our assignment. So you guys all know what an absolute value graph looks like by now, I hope. But if you have to graph some wacky absolute value graphs that have like different transformations in them, you can find absolute under the math button. Go arrow your right arrow over to the number category, and it's the first option at the top, ABS. And then you can type in whatever you're taking the absolute value of inside of parentheses. All right. So there's my natural log function, and there's my absolute value function. All right. pair up, group up, however you'd like to. Get started on these. I'm going to start calling folks over to my desk. I would like you to bring me, please, your the handout from the first day of class. It's got some factoring and quadratic function stuff. And then your 2 assignments